Okay, boys and girls, good day. I hope that you're doing your work step by step each night. If you do a little bit each night and keep up with these videos and the work in your homework package, it shouldn't be too difficult to start preparing for your quiz on this next week and preparing for any questions that will appear on your final exam. I think I went through your final exam last night and I counted about 5 or 6 organic chemistry questions. Now, of course you'll have naming and drawing and organic reactions on your final exam, but there is one kind of question that you will receive as well on your final exam, and that has to do with rank ordering boiling points of different organic molecules. So today we're going to go over for about 5-10 minutes about how you would rank order molecules, organic molecules, in terms of their boiling points. Okay? So, what would you be expected to do on an exam? Okay? Well, you're expected to know trends in boiling points, not absolutes. Okay? So there's no kind of mathematics that we can use to determine the exact boiling point of different organic molecules. But we can make good guesses to kind of order them from the smallest boiling point to the largest boiling point. If you want to actually determine what the actual boiling point is, then what you need to do is conduct an experiment. That's a laboratory procedure. Okay? So what you'd get is a question like this. Okay, so you've got 4 different molecules, and you would have to say, order these in terms of smallest boiling point to largest boiling point, that kind of thing, and provide a reason for your ordering as well. Okay, right here it does say that determining the exact boiling point can only be done experimentally by measurement. So there's no kind of mathematical formula we'll learn to do this. Okay. If you kind of understand these 3 key trends that we're going to go over, you should be able to answer more than 90% of these kind of questions that will show up on any kind of test or exam in the future. Okay? So how would we go about ordering something like this? Okay? Well, we need to look at different trends. Okay? So the first trend is, and this relates all the way back to September, when we were looking at intermolecular forces, IM forces. If you forget what those are, it would be maybe you might want to pause the video and go back through your notes and spend 10-15 minutes reintroducing yourself and reviewing or revising IM forces. So in general, as we've known since September, the stronger the forces you have, the higher the boiling point will be. Okay? And the stronger that will mean the higher the boiling point will also mean the lower the vapor pressure as well, because it will be harder for molecules to escape and turn into vapor. Okay? So if the molecular weight is pretty much the same, not too many big difference, then boiling point increases according to the types of intermolecular forces that are present. In general, there are 4 different types of intermolecular forces that are important. Okay? Number 1, ionic forces. Those are the strongest ones. So those are salts. So anything with a metal and a non-metal, in particular a metal with a halogen, those are those group 7 atoms, your fluorine, chlorine, bromine, iodine. Those ones have the strongest bond with them. Stronger the bonds, those ones will have the highest boiling point that require the most amount of energy to be able to rip them apart and turn solids into gases or liquids into gases. Okay, the next highest one is hydrogen bonding. A hydrogen bond is essentially, it's an electrostatic attraction between a hydrogen atom, which is essentially a proton because it only has 1 electron, and a very electronegative atom. For example, an oxygen or a nitrogen will work too. So anytime you have any alcohols or carboxylic acids, organic acids, or amines, those are the ones with the nitrogen and hydrogen in them, they will have relatively high boiling points. Not as high as ionic forces, but pretty high. Okay? The next kind is when we were talking earlier, right, with solutions and colligative properties, right, dipole forces. Those are essentially the ones that make up things like polar molecules that we were talking about before. These are ones where you've got a carbon that's bound to something that's more electronegative. So like an oxygen, a nitrogen, a chlorine, that kind of thing. And then, if you don't have any of those, all kind of molecules have these very kind of weak forces, intermolecular forces that hold them together. The rough reason for that is that electrons can move around freely, and sometimes they kind of momentarily clump up, and they produce a little partial negative charge in one area, a little positive charge in another area. It's unstable, it's always fluctuating and moving, but you can get these little partial charges that just appear and disappear just from the movement of negative forces. These are called London dispersion forces. They're present in all molecules. All molecules have these because the electrons are moving, but if you're dealing with, say, just a plain hydrocarbon, then this is going to be the only force that's present there, because you're not going to have any ionic forces, hydrogen bonding, dipole forces. Okay? So the thing to remember here is, if you've got four molecules that are the same, then you're going to look for ones that have ionic forces. They're going to have the highest boiling point, followed by hydrogen bonding, followed by dipole forces, followed by London forces. Okay? The next trend is the length of the carbon molecule, of the organic molecule. So with more carbons, you will actually increase your boiling point. Okay? Now this assumes that, okay, you've got ones that got similar intermolecular forces that are operating, but the only thing is different is the number of carbons. So you're going, say, from a pentane, a 5 carbon molecule, to say a hexane, a 6 carbon one. Well, the hexane is going to have a higher boiling point than the pentane will do. Okay? Why? Because the boiling point increases with surface area, which increases as the chain lengthens. So here you have different molecules, amines here, so they've got the same kind of intermolecular forces, IM forces that are operating in each molecule. The only difference here is the length of the molecule. So the longest molecule, the one with the most carbons, has the highest boiling point, which you can determine experimentally. Okay, and this goes through. If the forces are equal, that's what we're looking at. The third trend, so we've got intermolecular forces, which play a big role. We've got size of the molecule, and then we've got surface area. So linear molecules, these long chains, have the highest boiling point. Why? Because they have the most surface area. I think that just makes it easier for these intermolecular, London dispersion forces to operate. Okay? But as it becomes more branched and more spherical in a way, then the boiling point decreases. So, first trend, most important one to consider, intermolecular forces. Second one, length of the molecule. Third one, surface area. Okay. This one goes through about what boiling is and what it's considered, and we know it's boiling occurs when the vapor pressure equals the atmospheric pressure. And then from the beginning of the year, if you want to get something to boil at lower temperature, all you need to do is lower the atmospheric pressure, right? So you climb up Mount Everest, things will boil at a lower temperature. If you take a submarine deep into the ocean, right, you're going to need more energy to boil everything. So boiling is related to atmospheric pressure. Okay, so why? Because boiling point is essentially, it says here, and this is very important, boiling is essentially the measure of the energy that's required to overcome the intermolecular forces in a liquid, right? Stronger the intermolecular forces, stronger the boiling point. And that's kind of what we looked at here, right? So you've got your salts, hydrogen bonding, dipole, dipole, London dispersion forces. Okay. So here it goes through each kind of example of different ones. So if you've got kind of positives with negatives like this, especially where you've got a metal and non-metal, you are going to have some sort of ionic bonding. So lithium is your classic group 1 metal, and it's going with the non-metal. It's going to have strong ionic forces, right? Because that lithium is going to want to give up its electron, say, to oxygen. There. Okay. This is showing you that if you see any charges in the diagram, it's a good way of recognizing it. Ionic forces. Okay. This one is an example of hydrogen bonding. It's here, and hydrogen bonding is what makes water hold together, liquid water. Okay, it's what makes everything slide together. So we've looked at this with the polar molecule thing before, right? Water is a polar molecule. It's got this bent shape. Hydrogen has a partial positive charge. The oxygen has a negative charge. Why? Because there's a greater pull of that electron from hydrogen to the oxygen. That electron wants to spend more time with the oxygen. Well, what does that do? So that creates this hydrogen with a very positive charge. The oxygen has a very negative charge here. If hydrogen loses its electron, what does it have left that gives it that really positive charge? Well, it's got a proton that's left in its nucleus, and what it can do is kind of make like a, in a sense, kind of like an ionic bond, in the sense that it wants to kind of give its proton away. Here, it's the proton that's very highly positively charged is going to be attracted to this very negative oxygen. It's going to help bond that together through electrostatic forces, right? And then, you know, we can see these other kind of bonding too. So that's hydrogen bonding. So your strongest is your ionic bonding, followed by hydrogen bonding as well. So you're looking for hydrogens with oxygens, a big one too. You're looking with carboxylic acid groups, you're looking with amine groups, you're looking with alcohol groups that will do it. Okay. Just dipole, you're looking at things like just carbons with oxygens, that kind of thing, or nitrogens as well. They're weaker force, but they're still there. So it tells you, what are you looking for? You're looking for bonds between carbon electronegative atoms like oxygen, nitrogen, and your halogens, right? Because it will set up a dipole for that. And then you've got your weakest possible forces, and that's what it goes through here. The key point about London dispersion forces, right? These are these kind of momentary, fleeting dipoles that get set up in molecules just because you've got this kind of shifting, moving sea of electrons around everything. The point with this is they increase, these London dispersion forces increase with the number of atoms that are in the molecule. So surface area increases, or the chain of carbons increases. If it doesn't have any of these other forces, then the London dispersion force will increase as the length of the molecule increases, just because there'll be more electrons floating around. So you can get stronger, partial, temporary charges that get set up. Okay? So this gives you some examples of some partial questions. I think the questions on your exam for these are very, very straightforward. There's not a lot of guesswork. It's just going to use one of these to go, but if you can understand these questions, you'll have no problem with the easier ones that are on your exam. Your exam question was not meant to trick you. You will need to rank order them and explain on your exam, and that will be very important, okay? So here we've got 4 molecules, and we need to rank order them in order of boiling point. So you need to know which one has the lowest boiling point to which one has the highest boiling point. So one of the first things we can do is we can look to see if there are any intermolecular forces. You know, this one is just a chain of carbon atoms, okay? So this one only has those London dispersion forces with it, carbon and hydrogen, okay? This one has an oxygen in it. So this one is going to have probably a dipole force, that kind of thing, or hydrogen bond. This one is very long. It's got an oxygen in it as well, okay? This is a shorter molecule, but look, it's got a sodium in it. So that sodium is going to be capable of an ionic bond. So this one, all things considered, D is your best choice for the highest boiling point. So I'm going to say it for highest to lowest. So D at least is your first. It's got your highest boiling point of anyone there. Okay? Probably this one doesn't have any, you don't see any oxygens, any nitrogens, there's no metal in it. It's just length. I'm going to say that this one is probably your best bet for your lowest one. Okay, the lowest boiling point. So the question is, so what could we say about at least the second and third highest one? Well, so this one has an oxygen in it, this one has an oxygen in it. These are going to have relatively the same kinds of ion forces that operate, so we can't distinguish them in terms of ion forces. But what we would do here is in terms of length, how long they are. So this one has 1, 2, 3 carbons. This one has 1, 2, 3, 4 carbons. Okay? So 4 carbons, a longer chain, will have increased surface area, which will have a higher boiling point. So this one is going to be number 2, our second highest boiling point. And this is our third highest boiling point then. Okay, so the first thing really to do is look for those ion forces, and then probably you want to look at the length of the chains. Okay, let's look at number 2. So number 2, we should be able to recognize what this is. This is an aromatic hydrocarbon. It's a benzene ring. We can tell by these 3 resonating bonds. Okay. No.